Welcome everyone. In this video I will prove Gauss's law for electric fields. And I will make my proof for the special case of a sphere, but in a future video I hope to make a generalization of our proof. So let's get started. The formula that I want to prove, the law that I want to prove is, as I said, called Gauss's law, and it is as follows. The closed surface integral of the dot product of the electric field vector, so that's a arrow, dot product, as I said, ds, which is just a small area section, and I will get in more detail about what ds vector means. Well, this is equal to q inside divided by epsilon naught. Alright, so as I said, this is named Gauss's law. And it is specifically for electric fields. He also has another law for magnetic fields, which is more straightforward than this one. And maybe I can do a video about that one as well in the future. So to make our proof, to prove this statement, I will first draw ourselves a Q charge like this. This is a point charge, and we have a sphere around it. As I said, I am making the proof for the special case of a sphere, but this equation, this law is correct for any shape. So we have distance r, the radius r. This is a sphere, as I said. It looks like a circle because I am drawing on a 2D surface. Well, now you can see that the Q here is the Q inside that we have on the formula, and it simply means that when you have a closed surface like a sphere, you can just add the charges that are inside. Maybe you have Q1 here, Q2 here, Q3 here. All you need to do is you need to add them all if they are inside your inside your surface. These surfaces are called Gaussian surfaces sometimes. They can be real surfaces, or they can be, and most of the time, they are imaginary surfaces. But anyways, so this is what we have, QR. And now, the way I want to make the proof is, I will start with the left side. And I will try to arrive at the right side. So, let's find a formula for the electric field. At a point on the surface of our sphere, maybe at this point, or at this point, or at this point. It should be on the sphere, and it doesn't matter where it is on, because there is spherical symmetry, of course. This is a symmetrical shape. Well, this is equal to, using Coulomb's law, this is equal to a constant, Coulomb's constant, times q divided by the radius squared, and it is along the radius. This r hat simply means the unit vector along the radius, along the position vector. It has a magnitude of 1. It doesn't have a unit, surprisingly, even though it is called a unit vector. It just has a magnitude of 1, and it conveys direction. This is what we have, and for k, I will make this substitution, which is its actual value, 1 divided by 4 pi epsilon naught. Epsilon naught is just a number. It is a constant. It has units, by the way. It isn't like pi. It is, I believe, called permittivity of open space, something like that. But we don't need to get into it in this video. So if we substitute for k here, we have 4 pi epsilon naught r squared, and in the r hat direction. Now for ds is defined as a surface vector that is pointing away from the surface, away from the closed surface, and it is always perpendicular to the surface. So if we are at this point, it is perpendicular to the surface. Perhaps we are at this point, it is perpendicular again. It is always perpendicular. and this box with a dot inside of it means perpendicular. This is notation that I am using. Yes, so these are perpendicular. And to have a perpendicular line, for example, that is, to have a perpendicular line to a sphere, to a circle, you need to have it in the direction of the radius. So the ds, the surface vector, should be radial, which means it is value ds, and it is just in the r hat direction. Great, now we can evaluate our closed surface integral. So we have closed surface integral, and now I am making our substitution for E. Well, maybe let me write it one more time and then I will make the substitutions. Alright, now I am making the substitution for E. We have, as we proved here, as we derived here, using Coulomb's law, by the way. This came from Coulomb's law. Q divided by 4 pi epsilon naught r squared r hat. And now, this is important, that's why I'm writing in red. We have a dot product, which I went over in an old video, and you can watch it if you would like. We have dot product, and we are dotting it with ds r hat. Now, when you have a dot product of two vectors, what you do is you multiply their magnitudes, and then you multiply that product with cosine of the angle between the two vectors, and the result of a dot product gives you a scalar. So when we dot r hat and r hat, since the direction, since the angle between them is theta and it is equal to 0, we simply get 1. So r hat and r hat cancel each other. And as a result, we are left with the closed surface integral of q 4 pi epsilon naught r squared ds. It is a property of integrals that you can take the constants out of the integral, just like you could do in sigma notation, in summation. You can take the constants out. So, and I will write this a little above. So you can take q out, it is simply a constant, divided by 4 pi epsilon naught is a constant, and r squared is a constant as well, because for any point on the surface of our sphere, the radius value is the same. Their distance to the center is the same, because that's what defines a sphere. So we take r squared out of the integral sign as well, and we have the closed surface integral of ds. Well, this is, by definition, the total surface area of our sphere, because ds was a small, infinitesimally small area section, and if we add all of the area sections over the closed surface, over the entire surface, we will simply get the entire area. So what is the area of a sphere? It is simply 4 pi r squared. And so if we make this substitution, we have q divided by 4 pi epsilon naught r squared times 4 pi r squared. We see that 4's cancel, pi's cancel, r squareds cancel, and we are left with q divided by epsilon naught. Well, what is equal to q divided by epsilon naught? If you follow the equal signs, you will see that the integral that we started with is equal to q divided by epsilon naught. And this is it. We proved Gauss's law for a sphere. And as I said at the beginning, you can put a subscript inside here to represent that if you were to have more than one, q, more than one charge inside your Gaussian surface, then you would simply add them. For example, if you have q1 here and q2 here, q inside will simply be q1 plus q2. All right, Another representation of this law is also like this. You have sigma q divided by epsilon naught. Sigma simply means summation. You are adding all the charges that are inside your Gaussian surface. I hope you enjoyed this video. If you have any questions, please write them in the comment section below. I hope to see you in another video. Until then, take care.